Let me conclude this section 3.5 on some more examples of projection methods by a comparison where we compare Galerkin method and finite section method. And the starting point is the Galerkin method, where we have spaces x and y and bases in xn and yn. And let us extend this basis of xn to a basis of x and do the same on the y side. And then let's recall quickly how we can expand our equation ax equals b with respect to these bases of x and y. Well, of course, we can rewrite x as a linear combination of these basis elements here. And then let's rephrase this as follows. Well, first you bring b to the other side. Then you say that the null vector is the only vector that is orthogonal to the whole space y. And then you say that you're orthogonal to the whole space y if and only if you're orthogonal to every basis element of y. And then you just rewrite that in terms of scalar products. And then you split the scalar product here and bring half of it to the other side. Okay, then you plug this expansion of x in here. And of course use linearity of A and of the scalar product with respect to the first component. And that's your system for the infinitely many unknowns, alpha 1, alpha 2, and so on. So in the end we see that ax equals b expanded with respect to these two bases of spaces x and y corresponds to this infinite system here for the unknowns alpha 1, alpha 2, and so on, which are just the coefficients of the unknown vector x with respect to the basis of x. This system here, let's label it by star, looks a lot like the n by n system that we saw at the very end of the Galerkin method, that one here. Right, you have the same scalar products here, same scalar products here. The only difference is that this is n by n and the other one was an infinite system. In fact, if you look closely, then this is the n by n top corner of the other system. So let me label this one by G, or maybe by GAL for Galerkin. Then we can say that the Galerkin system is just the FSM of the infinite system that we denoted by star here, but that in the end is nothing but the original equation ax equals b. And the connection is getting even better because conversely, the FSM for an operator a from x to y replaces the equation ax equals b by Pna Pn xn equals Pnb with these truncation operators Pn. But these truncations here are just orthogonal projections of L2. Well, we obviously have to take a sequence space here, and let's take the same space x and y because we're using Pn at both places, onto the subspace where your sequences or vectors are only supported on the first n slots and 0 otherwise. Okay, and these are subspaces that you call xn, and the same yn, which are just the images of this truncation operator Pn. And to span these subspaces, you would just use the first n canonical vectors. And with this set up, you see that the FSM on your L2 space is a particular Galerkin method. Okay, so let's sum up. Every Galerkin method is a finite section method, and the finite section method on L2 is a Galerkin method, so it's almost the same. So our summary could say Galerkin is the same as applying the FSM on the Hilbert space little L2.